Good evening, everyone. My name is Andrew Fracknoy. I'm the astronomy instructor here at Foothill College in Silicon Valley, and it's a great pleasure for me to welcome everyone in the auditorium and everyone listening or viewing on the web to this special lecture in the 13th annual Silicon Valley Astronomy Lecture Series. These lectures are co-sponsored by 4 excellent organizations: NASA's Ames Research Center, the Foothill College Astronomy Program, the Astronomical Society of the Pacific, and the SETI, or the Search for Extraterrestrial Intelligence Institute. And we appreciate their help in bringing speakers and doing publicity for this lecture program. I'm delighted to say that tonight our speaker is one of the most distinguished astronomers in the United States, Dr. Roger Blandford. Dr. Blandford, a native of England, took his degrees at Cambridge University, where he was supervised by the Astronomer Royal, Martin Rees. He joined the faculty at Caltech in 1976 and was appointed the Richard Chase Tolman Professor of Theoretical Astrophysics, distinguished named chair, in 1989. In 2003, Dr. Blandford moved to Stanford University to become the first director of the Kavli Institute for Particle Astrophysics and Cosmology. At Stanford, he is also the Luke Blossom Chair in the School of Humanities and Science. He divides his time between the physics department and the Stanford Linear Accelerator Center, which is a national particle accelerator laboratory. His research interests include some of the strangest things going on in the universe: black holes, the origin of the universe, gravitational lenses, cosmic ray physics, and compact collapsed stars. Among the many international recognitions that he has received for his work, he has won the Eddington Medal of the Royal Astronomical Society and the Humboldt Prize. It's for me both a personal pleasure and a professional privilege to introduce to you, talking about black holes, the end of time or a new beginning, Dr. Roger Blandford.
Black holes have a very bad popular image. They are seen as agents of death and destruction, as torturers and annihilators. There have been several movies made about black holes. Here are 2 where the black hole casually ended the careers of several promising movie stars. There have been countless novels. Here the casualty was the English language. Black holes have inspired some of the most confusing scientific illustrations I have encountered, and some of the lamest cartoons. I'm entering the black hole now. Good grief, it's full of unmatched socks. There's a career here for all of you young people. You can't do worse. Here is a better book written by the late Carl Sagan, which was made into a famous movie. As is common in this genre, the plot became so tortuous that the only way the scriptwriter could escape was to invoke a variant on a black hole called a wormhole. This would allow you to pass from one place and time to something quite different. Sounds like a good idea, but the reality of wormholes is quite contentious. If you ever come across a black hole, as a physicist, I would not recommend the experiment. Here's an even better book from Dante Alighieri, Abandon Hope, All Ye Who Enter Here. It looks like a black hole to me. Black holes have been feared as threats to public safety. It was claimed that the large particle accelerators like this one in Switzerland would create black holes and swallow the Earth. Of course, this has not happened. And we knew that it would not happen because nature performs far more dangerous experiments all the time using cosmic rays. This is not the European debt crisis. People worry a lot about black holes. In short, they are thought to be bad. Now, I'm delighted to be here at Foothill College as part of the Silicon Valley Astronomy Lectures to try to redeem black holes, to persuade you that they are good and that they play an important part, an essential role in the life of the universe. I would also like to try and explain to you why physicists and astronomers like myself find them fascinating. It's time for me to start telling you a little bit about black holes. And for that I must begin with gravity. This here is Woolsthorpe Manor in Lincolnshire in England. It's where Isaac Newton was born and where he formulated his law of gravity. Those of you who know about mathematics may notice the integral signs he carved in the wall. That's actually a cruel joke because Newton's great rival Leibniz introduced the integral sign. That's Isaac Newton. This is a house very close to Woolsthorpe. It is where I was born. I boast about this to my students. They are quite unimpressed. What's that got to do with anything? A common rural myth is that Newton watched an apple fall from a tree and realized that the fall of the apple would be described by the same agency as the orbit of the moon, and he invoked an invisible gravitational force to do the job. So here in the language of mathematics is the force, which you give the symbol F, and it relates it to the acceleration and the famous inverse square law of gravity. These equations are the foundation of most of the physics that we know about until quantum theory came along. Now jump forward 250 years to 1915. Albert Einstein formulates his general theory of relativity. He combines three-dimensional space and time into a single entity which he calls space-time. He discovers that space-time is curved when there is matter around. In addition, he does away with Newton's invisible force and describes the motion of the apple and the moon as a straight line in a curved space-time. Here is Einstein's equation. It looks very different from Newton's law, but the outcome is actually very similar. And the small differences from Newton's description are today measured accurately. Einstein's theory appears to be correct to about 10 parts per million. We have no grounds for doubting it as far as it can be used. Within a year of Einstein's formulation of his version of gravity, a German soldier, Karl Schwarzschild, who also happened to be professor of astronomy, discovered a strange solution to the equation that I just showed you. Today we know that it describes a black hole. There was a special spherical surface that surrounded this black hole, which we now call the event horizon, and from which nothing, neither you nor I, nor even light, can escape. This is the point of no return. As I say, the event horizon. So there's a black hole, and surrounding it, shown graphically here, is this surface, this event horizon that the light cannot escape from. The black hole itself has mass, just like the sun, and the bigger the mass, the bigger the event horizon. Now what this showed, what Karl Schwarzschild here showed, was that mathematically black holes can exist. By the end of the 1920s, it became clear that the type of star known as a white dwarf star was supported by the same sort of electron pressure that we find in metals. A young student, I've shown here, Subramanian Chandrasekhar, and others realized that these white dwarf stars had a maximum mass about 1.5 times that of the Sun. And this white dwarf would have a size about that of the Earth. If the star became more massive than this, the electron pressure would be inadequate to oppose gravity. Moving forward in the 1930s, Landau, a Russian scientist, and a local scientist, J. Robert Oppenheimer, and others considered another type of compact star called a neutron star. And here the maximum mass is about 2.5 times that of the Sun. We know that these stars can exist because we see thousands of them around us as they speak. However, when, as commonly happens, compact stars have more than 2.5 solar masses, 2.5 times the mass of the Sun, they must collapse to form a black hole. In other words, black holes must exist. That's what the astronomers tell us. Actually, there is a complication here, and this caused much confusion. If we were to watch a star collapse to form a black hole, it would take formally an infinite time. So many scientists said that black holes should never form. The fallacy in this interpretation was exposed by this American scientist, John Wheeler, and his colleagues, who said that if you were unfortunate enough to sit on the surface of a collapsing star that was about to make a black hole, the black hole would, as far as you were concerned, form in a finite time. Less than a millisecond for a star, for a black hole of a mass of about a few times that of the Sun, say. Furthermore, the collapse would continue until gravity got stronger and stronger, and the laws of physics that we understand would break down. This anarchic state, this end of time, is called a singularity. There was much more that was understood around this time in the 1960s by Roy Kerr, a New Zealander, Roger Penrose, an Englishman, and Stephen Hawking. Sorry, they got superposed, the graphics there. Stephen Hawking, also an Englishman. What they discovered, they and their colleagues, was that black holes are really very, very simple. They are all surrounded by event horizons. The ones that show up in astronomy are described by their mass and their rate of rotation. No more, no less. We also learn how to do regular physics around a black hole. So to summarize, astrophysical black holes are characterized solely by their mass and how fast they are rotating, how fast they are spinning. They trap light, and these black holes cannot be escaped. So much for theory. Let's allow the astronomers to pick up the story. Recall that I said compact stars larger than 2.5 solar masses must be black holes. In the 1960s, astronomers started to be able to observe the sky, not just using optical telescopes or radio telescopes, but using X-ray telescopes. Here is a modern one, the Chandra X-ray Observatory, which makes exquisite images of X-ray sources in the sky and is named, as you might guess, after Chandrasekhar, whose picture I just showed you in a previous slide. The X-ray astronomers found many new sources, and in 1971 they found one in particular, shown schematically here. The imaging of X-ray telescopes is not that good, So this goes as a picture here. It's called Cygnus X1. Cygnus X1 was actually two stars, if you like, in orbit about each other, a binary star. One of them was just a regular star, and the other one was a compact star. It might have been a white dwarf, it might have been a neutron star, but it was weighed. It was possible to use the dynamics of Isaac Newton to weigh it, and it came in heavier than 2.5 solar masses. Therefore, it was a black hole. Black holes, therefore, do exist. You might be wondering why these black holes are observed in this way. After ending their stellar careers as lifeless corpses, why should they be reborn as X-ray sources? The answer is depicted here. What happens is that the star grows in size. There's the star here. As it gets older, it gets a little bit bigger. Sound familiar? The star grows in size, and the gas spills over to make a disk that swirls around the black hole. This disk is known as an accretion disk. And friction in this accretion disk causes the black hole to get hotter and hotter as energy is released. In fact, it gets so hot that it emits X-rays. Now, these black holes and their accretion disks are extremely efficient. Gravity power, as shown here, this gas spiraling inwards through that disk into the black hole, or it crosses the event horizon, it will be 100 times more efficient than nuclear power, and nearly 1 billion times more efficient than dynamite. So, if the world wants to solve its energy problems, all we have to do is catch a black hole. However, please do be careful. Now, there's a second feature of black holes being supplied with gas in this way that you can see depicted here, and I'll have more to say about this. This is a jet. These black holes not only have the gas going in, they make streams of gas, too, in opposite directions here, flowing out at very high speed, close to the speed of light quite commonly. These are called jets. So this is gravity power. Now, black holes and their disks have many other strange properties. One of these is that they can sing. They can, in fact, what's happening is they're oscillating with frequencies in about the kilohertz range that you can listen to. Obviously, you don't hear sound waves crossing interstellar space, but you can transfer the electromagnetic signals that you get into a noise. This is what you get. This is what it sounds like. This is what a black hole sounds like. I think it's musical. But I am tone deaf. There are many theories of how the black hole performs this trick, how it oscillates regularly, a bit like a clock, like a sort of bad clock. I'll shortly add another one to this, these theories. There we go. Black holes can also dance. Here is another famous source. It has the rather forgettable name of SS433. Again, there's a star and an accretion disk and two jets. The pair of jets make gas that streams out in the opposite direction with almost exactly 1/4 the speed of light. And what happens is that they spiral around, these two jets. So if you imagine that's a black hole, that's an easy enough thing to remember, and here are the two jets, then they spiral around like that, called precession. They do this in about half a year. Every half year they spiral around. And astronomers can watch them spiraling around like that. It's a bit like having a hose pipe and swirling it around. They make these sort of curving patterns. You can see it here. Here you can see the observations in X-rays. You can see this swirling pattern here. Remember this, because I'll come back to this a little bit later. There's a black hole there, There's this swirling pattern as you sort of two anti-parallel X-rays you swirl around. So this is the pas de deux. This is a dance of a black hole and its companion star. So, black holes are not just insatiable gluttons, parasites on cosmic society. They actually give something back. In particular, there are supernova explosions which are involved in the formation of black holes, and gamma ray bursts, which are very energetic. They create, sorry, I think I've got a slide out of order here. Let's just go on to the next one and then I'll come back to that one. If you're prepared to accept black holes in a metaphorical sense as alive, not dead, how are they born or reborn? It turns out that there are two ways that we're probably seeing black holes being born. The first involves special neutron stars called pulsars. So here we see two pulsars depicted, and these special pulsars, two neutron stars there, and what makes them pulsars is they make two beams of radio emission, like cosmic lighthouses. And when they're close together, they will orbit each other, and we know several examples of these, and we can weigh them. Now what happens with these two neutron stars is they spiral around each other, like that, round and round, and then they radiate what's called gravitational waves, and these orbits get smaller and smaller. They sort of shrink, the orbits, and then eventually you've got these two neutron stars, say 1.5 solar masses each, and they combine into a single object. 1.5 plus 1.5 equals 3. 3 is more than 2.5. Therefore, they make a black hole. So, black holes, systems like this, in 100 million years, are bound to make black holes. So not only can we say that black holes do exist, we can also say they will exist. There's a second way of forming them, and that is through supernova explosions. These involve the massive stars who have lived fast and died young, that have run out of gas. They have collapsed under the unforgiving pull of gravity. They have released energy and exploded as these supernova explosions. There is a very famous one that happened in a nearby galaxy called the Magellanic Clouds. It blew up in 1987, and people were able to see it easily with their naked eye, and a black hole was almost certainly formed in this system. The center cannot hold, mere anarchy was loosed upon the world, as Gates said. So we see supernovae across the universe. We see them back to the early stages of the universe, and they can outshine galaxies for a few months. Usually, they leave behind black holes. Occasionally, they leave behind, usually they leave behind neutron stars. Occasionally, they will leave behind black holes. And this is the second way of forming black holes in the supernova explosions. Now, what is remarkable is that these two ways of making black holes also do something else. It appears that they also create bright flashes of very high energy X-rays, which we call gamma rays. And these objects are seen, these birthing black holes, are seen as what we call gamma ray bursts. And the gamma ray bursts can also be seen across the universe. And more or less every day, a gamma ray telescope will be able to detect a new gamma ray burst. It makes a bright flash of gamma rays. We see it for a few seconds. In this case here, with the two, what we think of the two neutron stars, it is slightly less than a second. In this case here, it takes several seconds to be over, but in both cases we see these bright flashes of gamma rays, and they are called gamma ray bursts. So these are, if you like, the birth cries of black holes. I'm going to try and go back. This is the slide, sorry, that got out of order. So I said that black holes were just insatiable gluttons, they're parasites on cosmic society, and they're giving something back. The supernovae and the gamma ray burst explosions are very energetic. They create a blast that expands out to hundreds of light years. These are the remnants of supernova explosions that happened over the past millennium. In fact, they were observed as, in many cases, observed as supernova explosions, and the dates are known when they happened. These explosions do three very important things. Firstly, they create heavy elements, like carbon and oxygen and nitrogen and iron. These are the ingredients of life. They also disperse these elements into the space between the stars, perhaps ultimately allowing life, at least in its most primitive microbial form, to propagate. Secondly, these supernova explosions cause other stars to form and perhaps make their own planetary systems. And finally, these supernovae and their remnants, which we see shown, observed here, they make very high energy particles called cosmic rays. And so far as terrestrial life is concerned, they help bring about the mutations and the evolution that we have witnessed on this earth. So my contention is, in spite of all the bad press they get, black holes are ultimately very good for us. Let's get to this one. The black holes that I've discussed so far are not much more massive than the Sun. There is another type, a second type of black hole that astronomers commonly observe. And these are called massive black holes. And it turns out that essentially every normal galaxy has in its center, right in its very center, a massive black hole. Just like every atom has a tiny nucleus at its center. Our galaxy is no exception. It has a 4 million, I repeat that, 4 million solar mass black hole. How do we know that it's 4 million solar masses? It's because astronomers, like my colleague Andrea Ghez at UCLA, can actually observe the motion of stars going around them, just like Kepler could observe the motion of planets going around the sun. And you can use Newton's law again to measure the mass of the black hole. What we have here are the orbits. This is not just the orbits that have happened today. This is actually the orbits projected with great confidence until the middle of the next century. But we've seen enough of these orbits to be able to measure them and infer the mass of the black hole. But the black hole itself is very small, perhaps 10 times the size of the sun. And we know it is small. We have evidence that it is small because we see, firstly looking small, but also it varies. It varies very fast. In fact, in a quarter of an hour, that emission that you get, particularly in the infrared, coming from very close to the black hole is varying significantly. It's changing on timescales of a quarter of an hour. That says it must be very, very small. That confirms the idea that there's a black hole there. 4 million solar masses. Here's another galaxy, one quite close to us actually. It has the name Centaurus A. This has a black hole that's nearly 1 billion solar masses. Not 1 million, but nearly 1 billion solar masses. Here it is, seen with a Hubble Space Telescope right in the center. So there's a black hole there, and then there's a jet. You can see a jet coming out of the black hole, in the center of the galaxy. In this case, we see the jet using X-rays. We can also actually see it in gamma rays on the very largest scale. It's quite remarkable. So what we have is something very similar to what we found with the black holes with stellar companions, with star companions. There's a disk of gas in the middle of the galaxy. We observe it in the infrared, and it creates a pair of jets, which inflate two large giant bubbles. See down here. Now, where does the gas come from? It doesn't just come from one star. It comes from all of the gas in the galaxy that's pulled in by the gravitational force of the black hole sitting in the middle. Remember, this is nearly 1 billion solar masses, although it is very, very small. Here's another third galaxy that I'll show you. It's a bit further away than Centaurus A. It's known as M87, or perhaps more romantically as Virgo A. It was discovered by Heber Curtis working close by at the Lick Observatory on Mount Hamilton. He observed here, this isn't his image of course, but he observed something you can see in here just about, what he called a curious straight ray, apparently connected with the center or nucleus of this galaxy by a thin line of matter. This was in fact the first observation of a jet, which I've already introduced. Today we know that M87 is a giant elliptical galaxy in the center of a cluster of galaxies. And the nucleus of this galaxy contains a 6 billion, or 6 or 7 billion, not quite sure which yet, can't quite resolve that, solar mass black hole. And the straight ray, as I say, is a jet. So let me show you some more images of this. There's an image made with Hubble Space Telescope. There's an image made with Chandra Observatory, which I told you about. There's an image made with a radio telescope. It's the same jet seen throughout with different types of astronomy using different types of electromagnetic wave. There's a close-up of the radio. And down here is what until recently, about 5 years ago, was a spectacular tour de force of radio astronomers using a technique called very long baseline interferometry. Using this technique, they were able to see down close to the size of this black hole, at 100 times the size of this black hole, an image which is depicted, actually make an image which is depicted here using a radio telescope, and you can see on this very small scale, you can see the jets are still being formed. So the jets that are formed, we actually could observe them down to about 100 times the size of the black hole, and they were still there. So it's a phenomenon intimately related with the black hole. Now what I have to tell you is that in the last, about a few weeks ago, it was announced that you are able to see structure on even smaller scales in this source, and you can now see down to about 5 times the size of the black hole. So this is a remarkable technical tour de force. We're looking down. We aren't able to make an image yet on that scale, but that will come before too long. This is really quite remarkable. It's like being able to see atoms with an atomic force microscope, which some of you may know about. Let me say a little bit more about these massive black holes. I said 7 billion. Remember, the black hole in the galactic center was 4 million. This black hole in M87 was 7 billion. But it is not the champion. Work by my colleague Chung-Pei Ma at Berkeley has found the current champion, and that is argued to be weighing at 20 billion solar masses. 20 billion. That's heavy. Here's this is the Subaru telescope on Mauna Kea in Hawaii. It's a Japanese telescope. And one of the things that they have found is that they are able to find very massive black holes very early in the universe. And so big black holes exist when they themselves were very young, when the universe was, instead of 14 billion years old as it is today, was only 1 billion years old. So there's a bit of an obesity epidemic, and doctors have shown that older black holes are obese because they ate too much when they were young. So remember that, all of you under 18-year-olds here making too much noise. Now, I said we were feeding these black holes. We feed them their food that they like. It's mostly hydrogen gas. Probably not very appetizing to you or to me. It swirls around the black hole in a disk and makes jets, just like we saw with the smaller black holes. Here's a special case when you really feed this black hole very well. You give it all the food it could wish for. In that case, it makes an object called a quasar. And here's the very first one that was discovered in 1963 by my colleague Martin Schmidt in 1963. And what you see here is a star-like object which turned out to be the nucleus of a galaxy. And coming out of it is a jet. And right in the center of this is a black hole. And what was special about this discovery was that the emission, the radiation from this black hole was so luminous that it outshone, completely outshone, all the stars surrounding it. All the 100 billion stars surrounding this black hole and the galaxy that was around it were outshone by just a tiny black hole being fed with gas, no bigger than our solar system, right in the center of this black hole. And that was most of the power that was made by this galaxy. This discovery, remarkable, and we now know thousands and thousands of these quasars, and they radiate powerfully, and they do so because there's a black hole there and it is supplied at a prodigious rate with gas. I said that there were jets. Here are several of them. Here is a radio image of a galaxy, nearby galaxy, with a black hole in the middle of it. Here's a jet coming out of it. Jet is so powerful and so relativistic it goes way outside the galaxy. We look at it on smaller scales, we see there's a jet. And we look on a smaller scale, there's a jet. There's a jet like one of those Russian Matryoshka dolls. You keep on taking it apart and there's a jet. And as we've seen, if you go down to a size not much bigger than the black hole, there is still a jet. Here's the most famous of these jets associated with galaxies. This is called Cygnus A. It's the first of these big this is a radio image, the first of the big radio images that was discovered, associated with extragalactic sources. And there's the black hole in the middle of a galaxy there, and the jet coming out and inflating these two giant bubbles on either side of the galaxy. These jets that are formed can be impressively straight. Here's an X-ray image of one. Here is a black hole in the middle of a galaxy called Pictor A. And here's the X-ray image. You can see it's dead straight. That is true to a physicist. That is a truly remarkable phenomenon. It ought to be unstable. It ought to be dancing and whirling around all over the place, and yet nature seems to make it very straight. That is a real puzzle. Sometimes it isn't straight. Sometimes you get this hosepipe effect. In this case, there are two galaxies in orbit about each other. In this case, there are two jets coming out of two black holes in two galaxies about each other. In this case, there's one of these sort of SS433 type processions going on. So there can be lots of dancing going around with these massive black holes, as well as with the stellar black holes. Now, when I talked about the theory of black holes, I emphasized that the astrophysical ones were characterized by two quantities. A mass, is it big or is it small? And then a spin, is it spinning as fast as it can or just a little bit slowly, just turning a little bit slowly? This second quantity, called spin, was a bit of an enigma to the observers until fairly recently, because it wasn't quite clear how to measure it. Black holes are featureless. Their surfaces have no marks on them. If I look at the spinning Earth or a spinning top or something, I can tell how fast it's spinning because there's usually some mark on it to show it. Black hole surfaces, these event horizons, are smooth. There is no feature there. And so we have to use indirect arguments to find out how fast they are spinning. And one of them that can be used, this is a Japanese X-ray telescope that first did this trick, was to look at the emission from iron atoms in the accretion disk surrounding the black hole. And the iron atoms, if they were just sitting at rest, would emit a spectral line with a certain X-ray frequency or energy. You would just get one spectral frequency or energy. But if they're swirling around the black hole, there's a Doppler effect that works. And that Doppler effect means that the atoms that are coming, or ions that are coming towards you, have a little bit, the photons that they emit are a little bit more energetic, they have higher frequencies, greater energies, and so on. And the ones that are going away from you, it's the opposite. They have lower energies, lower frequencies. And so if there's a lot of swirling around, then you get a large range of energies. And the bottom line of this investigation, which the X-ray astronomers were able to make, was that the black holes that you see in many of these galaxies, not all of them, but many of them, are spinning very rapidly. Nearly as fast as they can do. We're not totally secure in that conclusion, but it's certainly a strong indication from this and other lines of observational evidence. This point, I want to bring together these observations and this theory to discuss how is it that black holes create the jets. We have a black hole in the middle of a galaxy, say. We have a disk of gas that is swirling around it. That disk of gas, perhaps like Saturn's rings, friction will cause the gas to move inwards and then cross the event horizon. Why should it choose so commonly to make these giant spectacular outflows, these giant jets, one going up and one going down? Why should it do that? Well, we think we're beginning to get an idea. We think we're beginning to get an answer. And to do that, we should turn back to the mid-19th century. Here's Michael Faraday, who discovered about electromagnetic induction. This was pure research, and when asked what use it would be, he gave two answers. One was, what use is a newborn child? The second answer was to a politician, I don't know, but one day I'm sure you will tax it. I think that is appropriate today for those who believe there is a benefit in basic research, not just in research that's equally important that's applied and was immediately going to help you make money or save the world. So, this is an idea that he had, which made into a spectacular application before too long, and it's associated with something which you might call Faraday's law, and part of what he discovered was if you had a spinning body, a conductor, some metal or something like that, and you had some magnetic field, then if the magnetic field, counted with rotation, the combination of magnetic field and rotation, would create an electrical voltage. And that electric voltage, it's called electromagnetic induction, can be measured and, of course, can be used to generate electricity and so on. It's not quite the way it's done in a power station, but the principles are very much the same. Now, a black hole also behaves like a conductor. It's not a perfect conductor. It's a conductor. It has a resistance. The resistance is about 100 ohms. For those of you who understand Ohm's law, V equals IR. This must come back as a memory to some from high school physics course or whatever. So we make a voltage, and we have a resistance of about 100 ohms, and so we can calculate the current that flows in this circuit. And those of you who remember some more of your high school physics can take the product of the voltage and the current to get an estimate of the power. And this is what we think is happening in these systems. I'll show you this cartoon again. This is just a cartoon. This is not a calculation. I think you can do it. Can you do it? essentially what we have here is an accretion disk in green and some magnetic field lines, rather like the magnetic field lines that are associated with pictures of the Earth and the iron filings around bar magnets and so on. So these are the magnetic field lines. And we spin these magnetic field lines because they're attached to the black hole and the accretion disk, and they make a sort of magnetic sleeve. Do that one more time. Make that sort of magnetic sleeve, and that magnetic sleeve defines the jet. I see I've got the colours wrong here. It's normal that fields are green, but in this case they seem to be red. I apologise. Anyway, so applying the ideas about Michael Faraday and combining them with the general relativity of Albert Einstein, you can make a similar type of electromagnetic inductor which makes these magnetic fields and creates this sort of magnetic sleeve that forms these giant jets that you see. Now what I want to show you next is not just a cartoon, but a simulation. This is one that's performed by my colleague, Jonathan McKinney, and I think it's the most detailed calculation that's been performed to date. It's a full calculation using the equations of Michael Faraday and the equations of Albert Einstein and combining them in an accurate numerical computation using some of the largest computers available in the United States. And what you can see, the magnetic field lines are now in black. You saw it getting started up. You can see it looking from above, and you can see the jet forming. Now, in a short while, we're going to change the polarity of the field. We're going to make a north field into a south field and a south field into a north field. And you see what happens is the field lines have just changed around, but we go back and making a jet. The jets are remarkably robust. But you'll also see something else. You'll see that these jets are not exactly anti-parallel. They're swirling, they're wobbling backwards and forwards just a little bit in a regular, almost periodic way. Why is it doing that? Well, we've got these strong magnetic fields, we've got these jets, and if we look at the accretion disk that's surrounding it, we can see structure in the accretion disk. And the best metaphor I can give you is something that the young people may not know what this is, but the older people certainly will. There was a craze a long time ago, about 50 years ago, for hula hoops. So you imagine hula hoops. I should have brought one, I suppose. I'm not sure I can still get one now. Do that. And that is what it is like. And that is the structure that is forming here, and it arises naturally. Now remember, I told you that black holes can sing. And what that singing is a regular sort of periodic oscillation of something. I promised you another theory of that, and this is it. That oscillation of the jet could well be the cause of the singing that we heard in those black holes. So, we talked about the environmental impact of the stellar black holes and their impact on life as we know it. The massive black holes also have an environmental impact. Here is one in a nearby cluster of galaxies called the Perseus cluster. There is a giant galaxy in the middle here, and there's about 1,000 other galaxies around it. We've just passed Halloween, but this may look like a Halloween mask to you. But in fact, what we've got here are these giant red bubbles that are created by jets. These are old jets that have created these bubbles. And what is happening here on the scale of a galaxy rather than the scale of a few stars is that the jets and the black holes are stopping all the gas surrounding the big galaxy. They're stopping it from falling in. They are preventing it from quenching the life of that galaxy, from smothering that galaxy, and they are creating new galaxies outside. So again, the black holes, this time the massive black holes, have a major impact on their environment. They limit the galaxy growth and they promote the birth of new galaxies. I've told you quite a lot about black holes in theory and in current observations. I'd like to finish this lecture by telling you about what is coming, what capabilities we hope to have in the near future to learn a lot more about black holes and related phenomena that we are discovering in astrophysics. The first opportunity is with new radio telescopes. And here are three. This is the VLA, the Very Large Array in the plains of St. Augustine near Socorro in New Mexico. It has been a wonderful workhorse radio telescope, the best in the world, for well over 30 years now, and it has recently been completely refitted to make it essentially into a new telescope, 10 times more capable than the old one. And it is starting to make new images of jets, and I just thought I'd show you SS433 again, as made with the new Very Large Array telescope. A second telescope is ALMA in Chile. This is in the Atacama Desert, and I've been there twice now, and it is, I think, the most beautiful place I've ever seen on the Earth. They're putting about 60 radio telescopes there to look not at radio frequencies here, but to look at much shorter wavelengths, millimeter frequencies, millimeter wavelengths, excuse me, and wavelengths much shorter, even smaller than that. And by combining this telescope with other similar telescopes in other continents, you can make the finest images to date of cosmic objects, and in particular of black holes. And we hope that using ALMA and other telescopes like it, we will soon be able to start imaging the black holes themselves, seeing down to the scale of the black holes. In the case of M87 or Virgo A, and in the case of the black hole in our galactic center. They have different masses, of course, but the one in the galactic center is much closer, and they have the same angular size. And we will hope to use telescopes like this to make what's called an event horizon telescope. This is a simulation, but to see if this simulation corresponds to reality. That is a very, very exciting prospect to actually image these black holes. Here are gamma rays. There is a telescope, a gamma ray telescope in orbit called Fermi Gamma Ray Telescope after the famous Italian-American physicist Enrico Fermi. Here's the rocket, which is carried out into space. This telescope, which is one that has been led by my colleagues at Stanford University, and it orbits the Earth every 90 minutes. And every 2 orbits, every 3 hours, it makes an image of the whole sky. And by adding those images up, superimposing them one after the other, it has been able to map the sky in gamma rays, and it has found nearly 2,000 of these jets coming out of the black holes in galactic nuclei, the massive black holes. It has also found much else besides. It's been wonderfully successful, and we're learning a huge amount about the jets and about the black holes by using observations with Fermi Gamma Ray Telescope. These are just mere gamma rays. Oh, there's the rocket. Let's go to high energy gamma rays. These are even higher energy than gamma rays, which some people were high enough. And here we don't have to go into space to observe these high energy gamma rays. What we can do is see the flashes of light as those gamma rays hit the Earth's atmosphere. When they come into the Earth's atmosphere, they make a sort of streak of light, which you can pick up with a sensitive telescope. And here's one. This is in Namibia. This is the Hess telescope in Namibia. This is me at the focus of one of those telescopes, taking a picture of me, taking a picture of, and so on. This is a corresponding facility in Arizona called Veritas. And using these telescopes, you can look at the jets and the accretion disks associated with the black holes, and you can see them vary, not just 15 minutes, like in our galactic center, in 1 or 2 cases on timescales as short as 2 minutes. This is something that's more powerful than 100 galaxies, 1,000 galaxies, and yet it varies on timescales of a few minutes. That's a truly remarkable discovery, and we are scratching our heads to try and understand it. So we've gone from these energetic gamma rays to the high energy gamma rays. Not to be outdone, let's go to very high energy neutrinos. There is a facility at the South Pole. It is called IceCube. And they try to find very high energy particles, not gamma rays, which are like supercharged X-rays, but neutrinos. You may have heard of neutrinos, and they can be created by processes associated with black holes and jets. And they have been searching for these now for several months. And they search for them, firstly by looking for them, because when they come through the ice beneath the surface of the South Pole, they make little flashes of light, so you see the lumiere. You can also listen to them because they make sound waves. And then finally you get radio bursts with them too as well. All of these techniques have been used to search for the high energy neutrinos, and to date we haven't yet seen any. So this has been rather disappointing. Unlike the other telescopes, it means you haven't actually found anything as yet. We hope we will one day, but so far not. Now, having gone from very high energy neutrinos, let's go to the ultra high energy cosmic rays. Here we have the cosmic rays, which were discovered as energetic particles 100 years ago this year by Victor Hess, after which the Namibian telescope was named. Here he is in his balloon going up, and his cosmic ray detector, his electroscopes and so on, to try and discover that these cosmic rays came from outside the Earth. He was a very brave man. He went up in the balloon. He knew he would return to Earth. Now, cosmic ray physics has advanced a lot since the days of Victor Hess. And the most exciting thing at the moment are the most energetic of the cosmic rays we have seen, the ultra-high energy cosmic rays. And they too make an optical flash as they hit the atmosphere. It's a different type of flash, but it's similar in principle, and it makes this optical flash, and it also makes lots of particles that you can detect in tanks of water and so on, but you can detect these cosmic rays. And the most energetic of these cosmic rays are made by, have energies comparable with the energy of a, so we say a bloop single. So it's a baseball hit into the outfield by a giant, appropriately enough here. Now, if we ask what these cosmic rays, these ultra-high energy cosmic rays were like when they were first created, they would be a home run. That's a baseball. It's a proton, has that same energy. Where can that come from? Well, it has enormous energy. Remember I said that there's this spinning black hole with a giant voltage? One of the very, very few places that has enough voltage to make a proton have the energy of a home run baseball is a massive black hole in the nucleus of a galaxy. It's not the only explanation, but it's probably today, it's one of the 2 best explanations left. And before too long, we will be able to distinguish this from the alternatives and see if it really is these massive black holes that are not only making the jets and these prodigious amounts of radiation throughout the whole electromagnetic spectrum, they are also able to make these ultra-high energy cosmic rays. And finally, there is a hope of seeing these gravitational waves. Remember I said the 2 neutron stars sparring together did so because they were emitting gravitational radiation. Well, we can also hope to detect that gravitational radiation directly. Here is a facility called LIGO. There are in fact 2 of them, and there are others in other continents. One in Louisiana, the other in Washington. And you look for the shaking around of mirrors, tiny, tiny motions of these mirrors that are created by waves that are made by stellar black holes or stellar neutron stars as they merge and other sources. To date, this facility has not seen anything because it wasn't sensitive enough to do it, but it is being retooled like the VLA, and in 2015 it will start up again, and it should then have the sensitivity to start measuring gravitational radiation from coalescing objects, including black holes and close by stellar objects. If we want to see the massive black holes create these gravitational waves, there are two more techniques. One is to go into space, and the other is to use the pulsars, which I told you about, which are exquisite clocks. And they get shaken around too by these gravitational waves, and they too may be able to make a detection of gravitational radiation. A very exciting prospect, a new frontier. We don't know what we will discover. So here are Isaac Newton and Albert Einstein. They taught us so much about gravity. Neither of them was able to explain how gravity works on the smallest scale. This is the ultimate question that's posed by the existence, of singularities inside black hole event horizons. I hope that one day someone, perhaps someone in the audience, will be able to understand what it means by saying time comes to an end. In the meantime, I hope that I have persuaded you that black holes are as fascinating, spectacular, and good for us, and they are demonstrably capable of a new beginning. Thank you very much indeed.
You had mentioned that a black hole is characterized by mass and spin. What about electric charge?
Excellent question. The question is, doesn't a black hole also have an electric charge? The answer is, in the world of theoretical physics, the answer is absolutely yes. And I was very careful, though, to say I was discussing astrophysical black holes. And what happens is that if you put any appreciable charge on the black hole, either a stellar one or a massive one, then it will immediately discharge. There will be lightning everywhere, and if, just like a cumulus cloud that gets charged up, it will discharge immediately. So in practice, astrophysical black holes are quite uncharged. But the charged black hole was in fact very important the progress of theoretical physics, because it opened the door to understand some very perplexing problems in theoretical particle physics by considering what happens around a charged black hole. So in the febrile imaginations of theoretical physicists, it was very useful. For astronomers, less important.
Can you tell the technician that he's got 2 microphones on?
Oh, there seem to be 2 microphones on it.
One of them has to be turned.
While waiting for the next question, let me say here's 2 books. I didn't recommend either, and I don't get a cut on them, but I recommend them to find out more about black holes. And then I'm able to make available after tomorrow. There's a bit of embargo on some more movies like the one I showed you that are actually very interesting indeed. I can make those available at the end of this week. And they'll be on my website, which is shown there.
Shall I go?
Question over that side. Sorry, yeah.
Professor, pardon me, my voice has a bit of laryngitis. You mentioned the fact that the black hole is a constraint on the size of galaxies, but also that it promotes new galaxy formation. It's curious because I understand that in the early universe, some say that black holes might have been the seeds of galaxies, but is there any evidence of that today, that currently black holes are promoting galaxy formation?
So the question is, what happened in the early universe? What we do know observationally is that black holes formed surprisingly early in the universe and grew surprisingly fast. As I said, when the universe was only 1 billion years old, there were very massive black holes already in place. So it becomes a sort of chicken and egg question. Which came first, the galactic chicken or the black hole egg? And of course, the answer to that is the same as the developmental biology question, is that, of course, they both happen together. And so there's a co-evolution of the black hole and the galaxy. Sorry, I interrupted you.
Oh, no. Yeah. Specifically, is there evidence today that that process is continuing, where black holes are seeding new galaxies today? Is there, or within, let's say, the last few billion years?
Within the last few billion years, we do see structures around jets and so on that could be interpreted as dwarf galaxies in formation, which may well be triggered at this late time by the effects of the black hole. But most of what I'm talking about probably happened when the universe was much younger.
Can I just ask one more? Okay, is the constraint on the size of the galaxy simply the gravity, or is there something more like the, you mentioned the jet and the bubble and everything, are there other constraints on the sizes of galaxies other than just the gravitational attraction of the black hole? And I'll take my answer at my seat.
Okay, so why, this is again another excellent question. Why are galaxies the size they are? Why don't they keep on growing forever and ever? One of the things that there seems to be that there is a characteristic mass for a typical galaxy. It's a little bit more massive than the Milky Way galaxy, but not much, just a few times the mass of the Milky Way galaxy. And then it's rather not quite as many galaxies that are smaller than that, and not as many as you might expect that are larger than that. The reason why there may not be so many smaller galaxies is because what happens is all of these black holes in formation, these supernova explosions and so on, blow away the gas and stop the black hole from forming. So there are fewer of them. The reason why there may not be so many more massive galaxies is because the massive black holes in the galactic nuclei blow away the gas and arrest the infall of more gas. And so it sort of switches itself off and stops more stars forming, stops the galaxy from growing. So that, in qualitative language, is what we think is going on. It's an excellent question. Over here.
Yeah, a friend of mine told me that she was saying there's a black hole and then there's the Earth and the Sun.
I'm afraid you're going to have to speak. Oh, is there a black hole between the Earth and the Sun?
And that we're going to get sucked up?
If there is, I promise you'll be the first to know about it. But as far as I know, there can't be a very massive one because, of course, we know with exquisite precision the motion of planets and satellites around the solar system. And if there were any sort of appreciably sized mass orbiting there, then all of the predictions of where planets should be and satellites should be and so on, they'd all be wrong. And they are. So, fear not. I think we're okay.
Okay.
First of all, great talk. Thank you very much. My question is kind of a terminology question. What's the difference between a Schwarzschild radius and an event horizon?
Ah, okay. Another very good question. Terminology. The Schwarzschild radius is the radius of the event horizon that surrounds a non-spinning black hole. So there's this surface of no return, which we call the event horizon, and it has a radius. Now you might say, what, it's all curved and so on, what does radius mean? Well, what you actually do, it's really quite simple. You take the area of that event horizon, which you can measure. Now, be a bit careful doing this measurement, but you can do this measurement, okay? And that area, you just imagine it's just like a regular sphere. And you say a sphere of that area, what's its radius? That's what you mean by the radius of the event horizon. And that radius for a non-spinning black hole is called the Schwarzschild radius. And so, now the event horizon is the actual surface, if you like, that surrounds the black hole, clothes the singularity.
I have a question about the density of black holes, and it seems like they're sucking in matter. Are they primarily comprised of matter? And I guess in their structure, are they denser than a nucleus of an atom, or are they like the individual subatomic particles? Are they like denser than a proton, like they've been compressed protons and neutrons?
Very, very good question. Let me give you an answer. If you take a black hole and you say it has a certain mass, which you could measure by seeing how stars go around it, for example, and we say it has a certain size, which is the Schwarzschild radius, which we've just discussed in the last question, and I've got a mass and I've got a size, then I can use that as a sort of formal estimate of the density in the usual way. If I perform that calculation for a massive black hole in the nucleus of a galaxy, then the density that you get is the same as you or I, or a bucket of water, or my water here, something like that, 'cause that's all we are, more or less, the first approximation. And it's that same density, more or less. If I take a black hole, a small stellar-like one, it's close to the density of a atomic nucleus. So you see, your question has a range of answers that depend on the mass of the black hole. So the smaller black holes we see in astronomy are about as dense defined in that way as an atomic nucleus, and the larger one are about that dense. Now, if you say we perform the experiment of a thought experiment, if you like, of going across the event horizon and then approaching this singularity, then the density that you get as you approach that singularity is colossal. It is 10 to the 92 or whatever it is times the density of this water. That is why we don't know how to do physics at that scale. Quantum mechanics and gravity are equally important. We just don't know how to handle that. And so the density associated with the singularity is enormous, unimaginable, and very, very hard to understand what happens at that point. But if we just define the density by the event horizon, the mass inside it, and the size of it, then it's more reasonable. Over that side.
Thank you for a wonderful talk, Roger. One question I had, you mentioned earlier about a conundrum of a black hole collapsing, and in, I think, the 60s, John Wheeler solved it. If you're riding on a particle falling into a black hole, you pass the event horizon, and time, proper time is
finite.
Yes. From the outside, I've heard the opposite. Yeah. Black holes are called frozen stars, so you actually never see it collapse. But yet we see supernova explosions. So I've thought about it, and I can't seem to cross the understanding the paradox. Yeah. Can you explain it a little bit more?
Yes, I think that's a very good point, and I'm glad you picked up on that. If we perform this thought experiment of somebody falling backwards into a black hole, holding a flashlight, like that. I haven't got it on me. So here, holding a flashlight, like that. Then what you would see as a distant observer is you would see the light from my flashlight. If I say it was pulsing, for example, the pulses would come less and less frequently. That's what you would see. They would get redder and redder and redder. And then in a finite time, you would see the final photon. You would never see another photon. Now, in some sort of silly way, it would take an infinite time for me to cross the event horizon in your version of the coordinate system. But as far as I'm concerned, this all happened for a stellar hole, say, for example, in a few milliseconds. It's all gone. So what you're seeing is just a strange way of describing the geometry of the black hole that's geared towards your particular place looking at it. what Wheeler pointed out through analyses like this, that the correct way to think about it was something that really did form in a proper time, and your viewpoint was really illusory, and to all intents and purposes the black hole had already formed.
Thank you.
So a supernova explosion, of course, most of the activity happens way outside the event horizon, and so it's not affected by any of these considerations.
Questions about spinning. Why do they spin in the first place, and how fast they spin? Do they have a preference for clockwise or counterclockwise spinning? Can we tell?
Again, very good questions. There's what's called rather facetiously the doctrine of original spin. I think I put it on one of the slides. And that is when the black hole forms, it's like, you know, the skater and all of that, conserves angular momentum, spins faster and faster, it's going very, very fast. And that's where the spin comes from. Now that's possibly true, probably true, but it's not the whole story. It is also the case that black holes can be spun down by creating these jets. The jets take their energy from the spin of the black hole. That's the remarkable thing. The jets take their energy from the spin of the black hole and they spin down the black hole to get slower and slower and slower. But then, at a later time, when they stop having a jet, they've got this gas swirling around it like Saturn's ring. And the gas is moving in. It's bringing in spin with it. That spin spins up the black hole again. So a typical black hole, most of us believe, in its lifetime over, say, 10 billion years, a black hole, maybe in the stellar system, but more typically in the nucleus of a galaxy, is going to perhaps be formed spinning rapidly, and then it's going to grow and slow down and make jets, and then it's going to be sped up again, spin rapidly again, and growing in mass all the time. And it'll do this maybe 10 times over its lifetime. Slow down, spin up, slow down, spin up. That's typically what we think will happen.
I don't know. I understood that if you were out in space, you couldn't see a black hole because it's. But you were showing clouds of dust on the screen. Can you sometimes see a black hole through in the midst of dust?
Could you repeat the question?
I'm not sure myself, but it's whether you could actually see a black hole if you were there in space.
Oh, again, that's what you actually see, and that's why these graphic artists sort of get it all horribly wrong quite often. There's an effect which Andrew mentioned called gravitational lensing.
Mm-hmm.
And what that means is a ray of light gets bent when it passes through a gravitational field, rather like passing through a lens. Now, if that ray of light, if the gravitational field, is associated with a black hole, then the bending is as strong as you might expect.
I see, but
but if the ray actually goes into the black hole, it crosses the event horizon, it doesn't come out the other side. Okay?
No, so, I know not even light can escape from a black hole, but I'm wondering if they can be seen from.
Well, you can detect them. You say, can you see them? The way that you would suppose you were a safe distance from a black hole, and you were looking at a field of stars behind them. Then what you would see is a distribution of stars that was very characteristic as a sort of halo around the black hole, and then something missing in the middle. And that we can calculate very accurately. We know what we would see if we performed that thought experiment. So that's what you would actually see.
Oh, okay.
Okay, I understand that Stephen Hawking predicts that black holes have a temperature and slowly evaporate, and that the smaller they are, the faster they evaporate, and that a 2 billion ton black hole formed in the Big Bang would be about ready to explode now. Can you comment? Is anyone looking for those things?
Yes. I know about this. In fact, I was Stephen's. I had the office next to him when he was doing this work a long time ago, so I was very excited about it at the time. It was a fantastic insight into theoretical physics that a black hole had a temperature, and that temperature was actually determined by the gravity at the event horizon of the black hole. You can define the gravity, Newton's gravity if you like, the strength of gravity at the event horizon of the black hole, and that is a measure of the temperature. And as you correctly said, the smaller the black hole, the greater the temperature.
Yes.
And this was a wonderful insight, and it opened the door, like the charged black holes, to the solution of otherwise puzzling problems in theoretical physics. Does this have any basis in observational astronomy? The answer is probably not. It is terribly hard to imagine how those black holes could have been made in the early universe based on what we now know and didn't know in 1974 about the conditions in the early universe. So most of us are highly skeptical, but nonetheless, astronomers have searched. And one of the things I did to sort of follow up from this when I was much younger was to calculate what the spectrum in radio waves would be from an exploding black hole. And people have looked for those using searches of output from radio telescopes. They could even do it with the Allen array, for example. Even do it with the Allen array, and the have found nothing as yet. But it would be lovely to find something. For a while people thought gamma ray bursts might be these, but it became pretty clear that they had nothing to do with these exploding primordial black holes. So my answer is probably not, but I would love to be proved wrong.
Thank you.
Over there, perhaps?
Yeah, great talk. Could you say something about the status of the debate over the entropy associated with a black hole, or the second law of thermodynamics?
Right. Okay. Not sure it's a debate. I think it's, well, at some level it's a closed question. Associated with the temperatures, there's a physical thermodynamic quantity called entropy. And a scientist called Jacob Bekenstein had another insight that was a sort of complement to Stephen Hawking's one. That the area, which I just mentioned, of the event horizon, I said you could define this area of the event horizon, that is the entropy of a black hole. At first it was just a metaphor, it was just, well, it's a bit like entropy. And then when Stephen Hawking got his wonderful results, it's just like it is an entropy. And entropy, as you know, must always increase. And this is the corresponding part of that is the area of an event horizon must always increase. And so what Stephen Hawking and Bekenstein and others were able to conclude was that when, for example, we extract energy from a spinning black hole to make these jets, we reduce the mass, that's where the energy comes from, E equals mc squared, that's where the energy comes from, but we increase the area. And we can do that with a spinning black hole. We can make the mass smaller, but the area keeps on increasing. And that's the way we think we make those jets.
Thank you.
Excellent questions. Thank you.
The era of quasars seemed to be kind of like a calling card announcing the existence of black holes in the early universe. Any speculations as to how black holes actually did form in the early universe in the short time period right after the Big Bang?
Yeah. There are speculations, and I think we're learning about that. I don't think we have the full story by any stretch of the imagination. But as you can probably imagine, there are two ways to make a billion solar mass black hole in the early universe after a billion years, say. One is to start off with a very small black hole and keep on growing, keep on feeding it, and then it grows like a baby, it gets bigger and bigger and bigger. That's one way. Another is to have a collapse of a huge amount of gas all at once, all falls like that. Okay? Now that second, say, 1 million solar masses of gas all collapsing all together like a giant supernova explosion or a giant gamma ray burst. Now we see the supernova explosions associated with stellar masses. They're pretty impressive objects. Suppose there were 1 million solar masses of gas that made a big black hole, just like a giant supernova, 1 million times as powerful. Do you think an astronomer would have missed that? They may be dim, but they don't. It may be dark at night, it may be cloudy, but they would not have missed that. So most of us think that it doesn't happen quite that way. That instead, you make the black holes from rather smaller seeds. They grow very rapidly, but gradually, not all in one great big go, but gradually over, say, 1 billion years. And that's the way that the black holes grow, and they do it together with the galaxy, with the surrounding galaxy, and they influence each other. The galaxy provides the food for the black hole provides the outflow, the winds, the jets, and so on, the radiation that modulates and moderates the formation of stars. And it's this symbiosis that probably happens in the formation of galaxies and the corresponding evolution, in the formation of black holes and the corresponding growth of galaxies. And I suspect that my colleague Sandy Faber will say something about this when she comes to talk to you in January. Okay, 2 more questions. So over there, I think it's this side.
I've heard that black holes can lose mass gradually through the process of Hawking radiation. How is this possible if nothing can escape from a black hole?
The Hawking radiation is only relevant for these tiny black holes. Typically they're as massive as a big mountain, which is small by a stellar scale. So a tiny black hole is the only type for which Hawking radiation is astrophysically important, and I've argued that in fact these are terribly hard to form and with no evidence that they actually exist. But if we can talk about this from the point of view of pure theory, and what happens is that the statement that nothing can get out of a black hole is not true of an unspinning black hole is not true when you include quantum mechanics. All of those statements were made in the context of Isaac Newton's, if you like, and Albert Einstein's classical physics. They were not made in quantum mechanics. And what you can do in quantum mechanics is you can imagine a pair of particles, a pair of photons if you want. One can go into the black hole, the other one can escape. You can get some radiation out of the black hole that way. And so it's really the magic of quantum mechanics that allows these tiny black holes to radiate.
But if you have a pair of virtual particles arising and one of them falls in, that's still something being added to the black hole, right?
Yes, but it can still radiate and it will lose mass. It will radiate away and lose mass. So yes, it has something added, but they're virtual particles. And then when you do the accountancy at the end of this, you end up with a balance sheet that has the black hole with less energy and less mass.
You didn't answer the question. Do they all clockwise or counterclockwise?
Oh,
or both?
clockwise or counterclockwise? Well, in the northern hemisphere, no, okay. Like the block hole, yeah. No, there is no preferred direction. You have to think about it. If you looked at it upside down, you know, what you might think was clockwise and counterclockwise and so on. So there's really no preferred direction of spin. I think if you want to relate it to something, and this is serious, a lot of these galaxies, you can see they themselves are spinning. And so the question is, do the central black holes spin at the same rate as the surrounding stars and gas in the galaxy? You might expect that to be the case, but the evidence for that is actually not strong, and we suspect that they're probably not very well related. This is one of the sort of very interesting questions that's associated with how do the galaxies evolve and the black holes vary with time, is the relationship between the direction of the spin of the galaxy and the spin of the black hole? And that may be what you were talking about. And there, the jury is still a bit out. We do know something about that observationally, but the jury is still out on that one. It's a very good question.
All right. Let's thank